Okay, hello everybody. Welcome to today's seminar. Today we are having Georgios Karananas, who after doing his undergrad in Athens did a PhD at the École Polytechnique Fédérale in Lausanne, in France. And after a postdoc there as well, he has been working in Munich since 2017. We have the pleasure of having him here today. And
pleasure is all mine. I really appreciate this kind invitation to give this talk. The title you can see here. But okay, what I will discuss is how conformal symmetry may turn out to be an important ingredient when it comes to harmonic analysis between symbiosis between gravity and standard model. So what I will talk about is mostly based on works made with Mikhail Saposnikov, Andrei Schering, and Sebastian Zell. As well, I've put lots of input, and this is heavily influenced from works by Sasha Monin, that is in South Carolina, Javier Rubio, you had him here, now he's in Madrid, Volodya Kazakov from Paris, and Marco Michel from University of Ben Gurion. So this is the rough outline of my talk. First, I'm going to give you an introduction and, mostly phenomenological motivation of why we do what we do. Then I'm going to highlight the possible relevance of scale and conformal symmetry in such consideration. I'm going to turn to the important role gravity plays in all these constructions. Then I'm going to quickly show you how a scale invariant universe looks like and why it may be very interesting. And before concluding, I'm going to briefly talk about the self-consistency of these models. So we have the standard model of particle physics. The way it was conceived in the 70s is a success story. Okay? Apart from describing a plethora of phenomena in the microcosm, the theory is complete. We have the Higgs boson observed almost 11 years ago. What we have not observed yet so far are convincing deviations from standard model at particle physics experiments. And there are also indications that standard model can be a well-defined, self-consistent effective theory, which is valid up to energies at least Planck scale, very high energies. So the logical thing to ask at this point is whether we have in our hands the final theory of nature. That all varies. And of course, we know the answer to that. It's negative, and the indications are rather compelling. So first of all comes observational point of view. We have standard model and you put it in any astrophysical or cosmological background, and it fails to accommodate well-established experimental data, associated with neutrino physics, rotation curves of galaxies, baryon and symmetry. And although the above can presumably be addressed with right-handed neutrino, then there is homogeneity in isotope of the universe at large scales. And in the present context, I'm going to show you that this is explained via an inflationary epoch in the early universe driven by the Higgs field. It's an unavoidable consequence of this framework that I'm going to introduce and discuss today. Now, going to the theoretical point of view, the standard model, among others, suffers from two issues, fine-tuning issues. I'm not calling them problems purposefully because they are not problems. They don't jeopardize self-consistency of the theory. It's just indications of that we don't yet see the full picture. And this is the cosmological constant and hierarchy issue, which corresponds to the incredible smallness of the vacuum energy and the Higgs mass as compared to the Planck scale. And especially for the hierarchy issue, there have been various ingenious proposals to address it. The most important ones is the low energy supersymmetry, composite Higgs models, and large extra dimensions. And although, the details differ, all these approaches share a same feature. And the same feature is presence of new physics right above the electroweak scale, such that the standard model is sealed from whatever high energy effects there may be. But you see, the logic, this whole assumption is where the problem starts, because so far we have not observed any deviation from the standard model of particle physics experiments, and at energies that should be, that these proposals predict new physics. So what I'm going to discuss now is how we can put at use this tendency nature shows to be liberated from scales. Okay, and let me be specific what I mean. Take standard model classically, and forget even about gravity. Then there is only one dimensional full parameter in the action of the theory, and this is the Higgs mass or its expectation value. Now put this to 0, and we have invariance under the full conformal group. For the non-experts, there's nothing to be worried about. It's Poincaré transformation, the standard relativistic invariance of the theories. And on top of that, there are rescalings of coordinates by constant or space-time dependent factor. So I've stolen from somewhere this grid, this illustration of a grid. Okay, this is the original, this is a dilatation, so you zoom in, and a conformal transformation, you zoom in, but you also rotate. Okay, but angles are exact, so causal structure does not change. Now, and the question I would like to first formulate and then try to answer is whether theories invariant under conformal group, that is conformal field theories, play a fundamental role in particle physics. Okay. Now, before going there, we should first understand what it means for a theory to be invariant under scale of conformal transformation. And this has some peculiar implication. First of all, provided that there exists an action that captures the dynamics of said theory, it cannot contain any dimensional parameter. And on top of that, such theories do not have a clean-cut particle interpretation. Okay, the spectra are continuous. Okay, so on the other hand, we have nature, that is standard model, that has both dimensional parameters, of course, particles. So at least at first sight, it seems that okay, we're maybe heading down a dead end. And this is, of course, a premature conclusion, very premature conclusion. Symmetry, the important point to understand is that in one way or another, the symmetry must be broken. Okay, because I want to paint a picture that is phenomenologically viable. Okay, this is first requirement. And also, I want this picture to be complete. Okay, and any complete picture of, that tries to describe our world has to have gravity incorporated. Okay, and it's the mere presence of gravity that breaks conformal symmetry. Now, this breaking can be effectuated in two different ways. Either in a maximally brute force manner, that is, you take standard model with a Higgs mass to 0, in a way that the scale n conformal symmetry is broken. Okay, so m Planck scale appears explicitly in the action. And then there is what I call a maximally consistent manner, although there is nothing inconsistent with the brute force manner. It's just okay, for a lack of a better alternative word. And maximally consistent is what I mean is that you copy conformal standard model to gravity, either in a globally scale or a locally scale invariant manner. Note that when discussing about gravity, we should be very careful what we mean about conformal symmetry. There is abuse of language. There is no conformal symmetry with dynamical gravity. There is Weyl invariance or global scale invariance. Weyl invariance is the gauge dilatation, what normal people mean, say conformal. Now, first I'm going to focus on the maximally brute force manner, how gravity enters the game in this way, so scale symmetry broken explicitly. But the statements I'm going to make are going to be quite general, so applicable to both situations, but then I'm going to particularize to the scale invariant situation. So this is all nice and okay, words and hand-waving arguments, but okay, we need to do physics, and to do physics, we need to write down action, okay? And to write down the action, we need to particularize on what we mean by gravity. And for me, gravity is something that captures the dynamics of a massless spin-2 field. That's it. No modified gravity. I don't want to enter the minefield of this stuff. Okay, that's my only requirement. Okay, this translates into having only operators that are not of mass dimension greater than 2. In standard metric gravity, this means that I only allow possible cosmological constant and Ricci scalar, nothing else. No Ricci square, no Riemann square, no Gauss-Bonnet, nothing like that. And then, as I already said, okay, I want my matter comprise only standard model, there is nothing else, presumably some free right-hand neutrino, but this is again different story. And then I want the only dimension of the parameter to be equal to 0. And I also want to have a portal between gravity and matter. And for that, I'm going to impose that my requirement is that this coupling should not happen with operators that are mass dimension greater than. Okay? This is a logical requirement, can be relaxed, but I mean, what I described here, it's naively simple. Okay, so take standard model. This dots stand for the standard model, the fermionic and gauge content. This is the Higgs field in the unitary gauge H, the standard potential term, the kinetic term. There is no expectation value. There is no mass term for the heat. This is what I will eventually identify with the Planck mass, and I allow for an operator coupling Higgs field to the gravitational Ricci scalar. Okay? R, of course, is the gravitational, it's the scalar term. Okay, that's the only thing I can write down. Now, what people, there appears to seem some misconception. This guy is a rather non-trivial modification to dynamics of the theory. Okay, and kicks in at energies which are relevant for the early universe. It kicks in when this term wins over the Planck, the M square. Okay, because it's a kinetic mixing. This don't forget, it's kinetic term for gravity. Okay. So when I introduce this guy, what I practically do is I modify the Higgs and the graviton dynamics. I mix these guys, and this mixing is operative at very high energies, and actually is what enables one to inflate the universe with the Higgs. Okay, and this was understood by Besrukov in his project of 2007. Now, what I'm going to explain is that, what I explained is that in this case, Higgs inflation, what is called Higgs inflation, is inevitable. Now I'm going to argue that the success of Higgs inflation is also inevitable. And the way to understand it is very, very simple. So we get rid of this, how to say, complicated mixing term here. It's naively deceptive, it's called right now. Okay, it's again, kinetic mixing. Kinetic mixing is non-trivial modification to dynamics. But once you untangle this mess, by doing what people usually call Weyl scaling, you end up with something which is highly suggestive. So you have a field that to make it canonical, you need to use an exponential map. But once you use an exponential map, you find that the potential of this guy is exponentially flat. An exponentially flat potential means exponentially small deviation from exact de Sitter. Constant means exact de Sitter. Some small correction means almost exact de Sitter. Okay, and almost exact de Sitter is bullseye. Okay, is done. Okay, because what we care about in inflation is the height of the potential, roughly speaking, and the slope of the potential. Height of the potential, I use psi parameter fixed, and once this is fixed, the slope follows because it depends on this kappa parameter that is a function of psi, and it's uniquely fixed to be right in the where it should. Now, we can understand from completely symmetry arguments why it's guaranteed to work. It's guaranteed to work, and not only work greatly, is that the theory initially exhibits some approximate scale symmetry, okay, broken slightly by this term. Once this is the case, everything follows. Then you have the symmetry, the cosmological evolution breaks it spontaneously. Higgs is a pseudo Nambu-Goldstone mode associated with the broken symmetry, means that is approximately shift symmetric, and approximate shift symmetry can only be broken exponential, and this is what guarantees this excellent agreement with observation. And this is fantastic, okay? So everything fantastic comes, with a price. And okay, where is the catch? Okay, and there is a catch, and there is always a catch. And the catch here is the fact that what I described is not unique, okay? And the fact that it's not unique is associated with a built-in, how to say, prejudice that we have about when thinking about gravity in terms of metric and Einstein theory, okay? Because the proper question to ask here is which gravity are we talking about, or better say, which formulation of gravity? Although this appears to be, I would say, an irrelevant question sometimes, because metrical theory, you may have heard these words, I mean, I just put it there, to show you figure that I'm proud of. But okay, metric affine gravity, Palatini gravity, teleparallel gravity, Einstein-Cartan gravity, metric gravity. These are one and the same thing, okay? Because GR, so the moment I require that my particle spectrum only comprise massless graviton, it doesn't matter what field description I have, I'm always going to end up with general relativity, okay? So why would I care? I care because the formulation matters as long as matter is present, okay? and matter fields, okay? Because in the absence of matter, the above are completely equivalent. There's no point in discussing metric affine, Einstein-Cartan, Palatini, everything is one and the same thing. But in the presence of matter, that is standard model in my case, they're not equivalent anymore. Okay. This is important to understand. And in what follows, I'm only discuss the situation with Einstein-Cartan gravity, because I'm a particle physicist, and this is the closest it gets to my mindset, okay? But this is my choice. All the statements are equally applicable to this teleparallel or Palatini, etc. Now, the only thing that I need you to remember, you don't even need to care about this Einstein-Cartan, is that usually when deviating from metric gravity, we have at our disposal more objects of geometrical origin to write down in the action. So in this particular case, apart from the standard curvature that involves derivative of the connection, I also have derivative of what is called tetrad, okay? So torsion, this is what we call torsion. Again, details are not relevant. The important point is the following. So imagine that I want to describe, to construct a theory, purely gravitational theory, forget matter, that only propagates a massless spin to field. In Einstein gravity, I would write possible cosmological constant plus the richest scalar term. That's the only thing that complies with my need. Now, in Einstein-Cartan version, I should write 10 terms, okay? Cosmological constant, okay, irrelevant. Then there are 2 curvature scalars, 2 derivatives of torsion, and 5 torsion square terms. Of course, appearances here are very, very deceiving because for connection, omega and torsion are not dynamical fields, okay? Not dynamical means that I can integrate them out, find equations of motion. This is an easy algebraic exercise. And what one notices is that, okay, the connection is actually the Levi-Civita connection. So omega is the derivative of the method. You plug it back into action and you recover what you should expect, right? Cosmological constant and scalar curvature. Nothing more than Einstein-Hilbert action. Now, with matter fields, the logic is exactly the same. It's just that now we're going to have more ingredients, okay? And the consequences will be rather non-trivial. Now, what it means in terms of equations, what I'm saying now. We're going to have now more couplings to the curvature scale. I took size here. Okay, this is a very schematic form. I refrain from using explicit equations because okay, they don't serve any purpose at this stage. Then 2 terms of coupling Higgs to the derivative of torsion, 5 terms coupling torsion with Higgs with torsion square. That's all. Okay. Now, what I've managed to do by doing that is I've modified the way Higgs field interacts with gravity. Okay. However, what I've managed to preserve is this approximate scale symmetry that I have. And once I have approximate scale symmetry, I'm guaranteed to work. Okay. Because what I practically changed the slope of the potential. Okay, this kappa parameter that I had uniquely fixed before in terms of psi, now it's a more complicated function of all the coupling constants that appear in my theory. Okay, so I can still have successful inflation, but now the amount of gravitational waves that I produce, that is the slope of the potential, is controlled by kappa, and this changes. So the picture I showed you before is modified as follows. So, okay, this is it's not very detailed. I made these plots. So my artistic abilities are rather limited, but the point is that, okay, we have freedom on the amount of gravitational waves, but why would I care? I mean, okay, I can reproduce metric Higgs inflation. Why would I need less or more gravitational waves? The reason I would like that is because what I said before was not complete, okay, about the role of gravity. I talked about the role of gravity, how it breaks symmetry, okay? The conformal symmetry, but this is not enough. We want to have a phenomenologically viable theory. So this breaking, it needs to be communicated to the particle physics sector, okay, right? And not only that, it must be done in a rather controllable manner. If I'm, to even start thinking about hierarchy generation and Higgs mass much more than Planck mass, and more specifically, it must be done so carefully such that I reproduce this 17 order of magnitude between the Higgs and the Planck mass. Okay. Now, if I try to do that perturbatively, I'm off by many orders of magnitude. No way that I can do that. So back in 2016, Sapoznikov and myself, we came up with this idea that some non-perturbative gravitational effect may be responsible for that. We didn't pursue it at that time, but later It was found again by Misha and his then student Andrei Skerry, a non-perturbative solution to this theory that allows you indeed to reproduce the Higgs mass from the Planck mass. And not only that, the way this splitting goes through is via this kappa parameter that controls the amount of gravitational waves. So here we have a rather unique situation. We have hierarchy generation, so we reproduce the Higgs mass, and at the same time we map it to the amount of inflationary gravitational waves that are produced. Okay, and this was realized by Javier, myself, and Anthony. Now, with that, I want to discuss what happens with a scale invariant universe. Okay, and how this should look like. First of all, why would I bother? Okay, I will bother about the situation where gravity enters the picture in a fully scale invariant manner, because things here become even more interesting. Let me explain. Okay? Now, a rather non-trivial statement, but follows trivially by doing dimensional analysis, is that in theories where you have full-scale invariance broken spontaneously, the vacuum energy vanishes automatically. This is aftermath of the fact that the potential is a homogeneous function of the field. So having spontaneous breaking means that this field gets non-vanishing expectation value, whereas its first derivative vanishes, right? And since the potential is proportional to the first derivative, the potential itself vanishes. Okay? And the reason this is interesting is that vacuum energy in the presence of gravity corresponds to the cosmological constant. Of course, you're going to ask me whether actually symmetry breaking configuration, or what I say here, flat directions exist. And the answer, I don't know, okay, to be honest. I don't know of any phenomenologically viable non-supersymmetric theory that allows for such natural conformal symmetry breaking. Okay? We have found a counterexample, which is non-supersymmetric, but it's rather exotic because it corresponds to some daughter theory of supersymmetric young Mills. And there are certain, non-trivial things happening there, which is a delicate interplay between large and limit. The fact that this theory doesn't have running couplings, it's a finite one. It has plethora of flat direction, but the most important one is that it's on Hermitian. Okay? And this is what stabilizes the whole business. Now, whether or not this is relevant for cosmological constant problem, I have to be very honest, I don't know. Okay, but at least it's worth looking at. We found one counterexample. There may be others. Okay. I don't know. I have mixed feelings about that. Mostly because I don't know what this self-protection mechanism, which is the biggest turn off with this theory. This non-hermiticity, it has to be replaced. Now, what would happen, again, equation-wise, if I combine the ideas of scale invariance and conformal standard model? That is, I put, apart from the Higgs mass to 0 from the standard model, I also put the Planck mass to 0. Right? That would be my starting point. I mean, naively thinking. Okay? So I write down what I presented before, but with m square equal to 0. And what I find is that in one try, I managed to ruin standard model, late universe, and early universe in one try. Okay, I didn't even have to try that much, because what I wrote here is the Einstein-Cartan version of induced gravity, specifically. Okay, so again, very complicated dynamics, at least at first sight, because of this non-trivial kinetic mixing that curvature quantities interacting with field bringing the game. Okay, I untangle the mesh, do value scaling, and of course I recover a field which is completely decoupled. At least it only, better say, it's derivatively coupled and interacts only gravitational via the rest of the field. So for instance, writing down the fermions in this toy model that I'm working, I see that it does not interact high field. In fact, it's supposed to be Higgs. This is clearly not viable. But also I see that the potential is constant, so I cannot even inflate with this guy. Okay, and again, the way to understand it is what I wrote here is a scale invariant theorem the cosmological evolution breaks the symmetry spontaneously, making the Higgs field or H field, whatever, into exact now Nambu-Goldstone mode associated with the breaking of the symmetry, and thus at most derivatively coupled to matter. And this is not Higgs. No. And this actually, okay, if I insist on having the symmetry, let's say, broken down to scale invariance, this is what what proves, quote unquote, the necessity of introducing an additional scalar field, what I call dilaton, what we usually call dilaton, in order to assume the role of the Goldstone mode. Okay. Now, when this is done, as I said, scales are generated by this guy, gets expectation value, then Planck mass is associated with this expectation value, and then the Higgs mass is generated non-perturbatively, probably. I mean, in this setting that I'm trying to push forward here, it's generated via this mechanism. And of course, that's not the only thing that the dilaton does. It can have an interesting role in the early universe because it can, again, a big quintessence-like field. Okay, because as I said, if you remember a couple of slides above, there is no constant vacuum energy in these considerations. Okay, so I need dynamical dark energy. Again, this is topic for another talk. I just present it here because it's an interesting consequence, and you get kind of for free this information. Now, you're going to ask me, okay, bring in a new field in the game, okay, desirable feature, some hand-waving arguments about vanishing vacuum energy may be interesting for cosmological constant issue, but what about inflation? Do you still get inflation? The truth is that, okay, there is too much freedom now, because what I do when I bring in the game the field is I practically non-trivially modify the kinetic sector of my theory, but still there exists a wide class of models with which are effectively, apart from being single field, also their predictions are identical to Higgs inflation. And it's exactly these models in which conformal symmetry is broken by gravity in around very high energies, and this requirement is actually a constraint of the curvature of this manifold, which coincides now with this control parameter kappa that I presented many times before. So what in this picture, I mean, it sort of completes the previous one because it gives, the real link between observables, geometry, and okay, hierarchy if one wants to push it a bit, more with this non-perturbative mechanism. Again, I'm repeating myself here because it's really worth, showing that the predictions, although the dynamics seems to be complicated, are really, identical, at least from observational point of view. Something that is guaranteed to me. And again, because good works need to be advertised, and especially when done by people that are here, Matteo Piani and Fabio Rubio have published recently work on Higgs dilaton, this kind of model that I'm pushing here, exactly Einstein-Cartan gravity, but deviating from this requirement of conformal symmetry, because, okay, practically what I discuss is scratching the surface, okay? There are many things that we still haven't studied, and I mean, at least in my opinion, it's worth having a look. Now, a zero-order approximation to the self-consistency of these theories is to try to understand whether or not what we're doing here is applicable. Okay? And let me explain. Whenever gravity enters the game, whatever matter sector I have, standard model, generalization of standard model, I'm always going to end up with a non-normalizable effective theory. Usually, we don't care about this because it kicks in at the Planck scale. Okay? And this is, I mean, something that we're agnostic as to what we need to replace the theory at that high energies. Okay, quantum gravity kicks in. I don't have much to say about that. The point is that when non-Newman couplings are present, what we effectively do is that we lower the range of validity of these theories, and this can be actually lowered quite significantly. Okay, so the decisive factor, whether or not what I'm talking about here is whether it makes sense to work, if it makes sense to even discuss these theories, whether the phenomena that I'm trying to describe take place at energies which are way inside the range of validity of this theory. Now, what is the crux of it all? Okay, what is the Achilles foot of this construction? Achilles foot. Let's forget about Higgs inflation, about cosmology, etc., and look at the vanilla standard model. Okay, and more specifically, let's focus on what happens with the longitudinal components of the W and Z bosons. Okay, now these guys, when they scatter, I put the final diagrams. The important point to understand is that Higgs field is a very important ingredient of the standard model, not simply because it gives masses to the parts, because it unitarizes the sample. This behaves badly. You see this is where this is a bad behavior. It grows with energy. It's not unitary, as we say. Now, it needs exactly the Higgs field in order to cancel this bad behavior. And this is again a delicate cancellation, and it's possible if and only if the interaction of the Higgs field with the vector field is of a very specific form. It comes from this covariant, from the covariant derivative and so on. Now, what I'm doing when I'm inflating with the Higgs is I'm neutralizing completely Higgs mechanism. Okay, because Higgs gets a large expectation value because the background is inflating, meaning that the gauge bosons that are of course there become super heavy. Okay. At the same time, what I do is, as I said numerous times, I'm identifying the Higgs field with a pseudo-Goldstone boson associated with the breaking of scale symmetry. Okay, and once this is done, at most exponential interactions can appear. Okay? But exponential interaction means that this kind of diagrams are very, very suppressed. I'd say I ruin the cancellation. Okay, and if I ruin the cancellation, eventually this guy will grow enough, and this is where my theory will stop behaving well. And this happens at this Planck over square root of psi is significantly lower than the Planck scale, but still larger than the energy available to the system, which is the Hubble inverse Hubble scale. Okay, so sorry, the Hubble scale. So everything is self-consistent. And then, okay, I also put this slide here simply to give you the big picture. In the low energy limit, there are, of course, again, the non-normalizability results to a tower of higher dimensional operators, again suppressed by a scale much smaller than in Planck, but now at the electrode vacuum, I'm well below this energy, so I don't worry too much about, this kind of stuff ruining self-consistency of the theory. And actually, yeah, this brought me to my conclusions. I think I'm ahead of time. So I've given you a picture of, at least, a largely biased view on why conformal symmetry may be important for having harmonic symbiosis of gravity and the standard model. In this particular setup, if inflation is what is responsible for allotropy and homogeneity of the universe, the Higgs field that is responsible for inflation, then in this construction is gravity that assumes the central role, okay, because it's responsible for breaking the symmetry, and then also communicating the breaking to the particle physics sector. Now, my considerations focused on Einstein-Cartan gravity simply because I like it, but these are applicable in a more or less straightforward manner to whatever formulation of gravity one wishes, as long as one does not, bring extra degrees of freedom of gravitational origin. If this non-perturbative mechanism is indeed operative, then one manages to breach the very late dynamics of the universe, which is a rather, non-trivial and interesting consequence, because the Higgs mass translates into the amount of gravitational waves produced during the inflationary phase. And then uplifting everything to a completely scale invariant framework may offer insight also on the cosmological constant issue. And that's at least something worth thinking about. Thank you.
Thanks very much for the nice talk. And yeah, we are a bit like, we have plenty of questions.
That was faster than expected. 40 minutes instead of
Perfect.
45.
Very nice. So, where do we start? Questions?
Question. You're using Einstein-Cartan for your texts, but in your action, you involve a couple. I mean, should a couple torsion to periodic.
Sure, of course. I mean, because for my discussion it's irrelevant. You see, I focused on inflationary dynamics, which is driven by Higgs field. But of course, I mean, in the full blown standard model, I would allow, because these are the rules of the game. Okay, I said that gravity and matter should couple with specific, let's say, with operators not of mass dimension not bigger than 4. And this complies, say, psi bar psi with torsion, complies with this rule. I would couple it, and then I would understand the consequence. Actually, people have done that quite in great details. Yeah, but I don't see why not. Yeah, sure. No, actually, I would insist that we couple torsion values, okay? Because otherwise, it's not, we're cheating.
I have a couple. One is a curiosity because I think I should know, but I don't. So I break one. Let's suppose that I break one of the rules you were imposing about the dimensions of the perimeter, because it's sufficient but not necessary.
The first human. Yes, sure.
To have just the graviton.
Yes.
Because you can put like body or stuff like that. I don't know with torsion if you can.
Sure. I mean,
but do you think it spoils the picture in any way?
It will. It will. No, again, depends on how you're going to do it, okay? So, say, again, let's take Einstein-Cartan specifically, because it's something that I can give you a concrete example, or Palatini. Okay, if you add R squared term, it also doesn't bring any new degrees of freedom in the game. Okay, but the way it's going to affect the scalar interaction, because also this guy contributes to the kinetic term of the graviton. It's non-trivial, okay? So I expect that there will be differences. I don't know to what extent this will affect the picture. I don't think that much, because still it's asymptotically scale invariant theory. So for sure it will be acceptable from observation point of view, at least in some domain of parameters. But of course, I mean, this is
fundamental level. I mean,
the logic is the same. The logic will be the same. But of course, if you start deviating from this, criteria that I posed here, it's I can't give you a general answer. It's on a case-by-case basis that one should study and understand.
Another one.
Okay, well, Kristen, no, maybe we can, maybe Kristen goes now, and then you go on.
I don't know if it was explained by your slope of the kappa parameter in the standard inflation picture. There's like the cosmological factor of the taking exponentially, and then like the end of inflation.
Yes.
How is that analogous in this case?
I mean, graceful, if there is graceful exit, sure. I mean, you end inflation, no problem. I mean, the potential at energies when the field is at around approach the end of inflation, okay, the potential becomes the standard m squared phi squared. Yeah, okay. This I only showed here. What is relevant for the? Sorry, I usually have this plot. The potential is exponentially flat, and then towards the end is the standard m squared phi squared potential. So there is no, what you're asking about graceful exit, there is nothing like that. It's everything works fine.
If there's a door, you want to do.
Yes. I produce whatever observed there is around the inflation and from what the end is.
Mateo?
Okay, I have another one. I mean, you kind of told it because at some point you mentioned the thing we were doing and you said that there can be deviation. But my question was when you do the generation of the X mass with this, it was like,
Yes.
so it's based on curvature in the picture. But as you were saying, we found that there are situations which is not actually curvature regulating the inflationary part. So
No,
do you know when and how this deviates and how it affects this?
I know. I mean, you see. So the moment so this is a very general situation, okay? I haven't assumed anything. The moment I assume that conformal symmetry, that my theory is conformal up to the Planck scale, say, where gravity kicks in and breaks in a scale invariant manner, the curvature of this manifold is fixed and it's equal to constant and equal to kappa. And not only that, it's this C parameter that you and Javier call in the paper that is usually there, it's fixed to be equal to 0 because I require conformal symmetry to be always broken at Planck scale. There is no, the curvature is constant, okay? It doesn't change. So it's always going to be a situation where you have a field of this form. The inflaton will always going to be dh over h squared. dh squared over h squared. So it's always going to be exponential. Maybe it's always going to be exponentially flat potential. It's always going to be spot on with observation, provided the slope is good enough. This kappa is good. So the larger the kappa, the best for us. And the larger the kappa, also the best for the generation. Of course, once you deviate from that requirement, having curvature to be always kappa and constant, then you end up with different kind of models like the one you studied with Javier with a cubic pole. Okay, but this lies beyond what I discussed. You don't have
So it's
conformal.
automatically excluded by the selection, by the way you are building.
Right. This is something on top. I assume that that curvature is kappa constant all the way throughout the evolution. This is an assumption. You didn't assume that. We didn't assume at the beginning of this thing. And once, okay, and if you don't assume that, you see that you can deviate from this behavior, and then there is not. It's not necessary that there is a link between curvature and observer and hierarchy.
Are there any other questions? Más a tu respuesta.
The prediction seems to be intentional.
Yeah.
One field.
Yes.
So in this way, so in priority for squared one.
Sorry. Okay.
In the field priority in this one, just the squared one in 2 dimensions.
Yeah.
Field fire because field the priority is
Yes.
fire.
Yes.
Then in the priority is
Exactly, because
squared.
once I canonicalize the variables, this is a mixed form. Okay, I didn't show it explicitly, but once I canonicalize the variables, I find that the coupled field completely without potential, and the field that a certain combination of fields that actually inflate. So I inflate only in one direction in field space. Think of it again, symmetry argument. Okay, I have a concept current associated with this scale symmetry. It's spontaneously broken, but it's there, the symmetry. Once this is there, the field is the current. Okay, the equation of motion for the field is the continuity equation. So it's conserved. I don't. I only practically inflate in one direction in space.
So something that you would depend on the question. So you say that this conformal symmetry for a specific value of kappa can be extended up to Planck scale.
Exactly. Yeah.
I just think in the sense that is interesting in the sense that still you will have any other sector here of that scale that symmetry and matches on the scale.
Yeah.
So at the end of the day, we will break the symmetry also in the scalar sector much smaller scale to look for next. Right?
I'm not sure I understand. So
Clearly the symmetry is broken at a much smaller scale.
you mean this in blank over square root of psi or
That
whatever?
is an
Sure.
unavoidable just because of the conformal factor. So then always we will break.
It's always like that, yeah.
Even if you're able to cure it in the scalar
Yes,
sector of
yes,
the
yes,
field.
yes.
So to do the tests, you will always permeate into 1%.
Yeah, but this is controllable, right? I mean, I know how to
Oh,
do
yes.
it. I understand. Yeah, it should be. Yes, yes.
Why
I want my
is
scalar
why is
sector to be,
why is
I mean, through loop effects, I know exactly how it's gonna come about, right? It's only gonna be in blank over square root of psi at some power. So I don't see why this is a problem. I don't want the scalar sector to break on formal symmetry either, because you see, that is the issue with this guy here. Once I relax this requirement, I cannot have this universality of predictions in inflation. As long as I fixed my curvature to be constant all the way, it doesn't need to be m-Planck, can be m-Planck over square root of psi. Okay? Can be.
it will just control what you are assuming exactly the what happens in that case and put it on.
Gauge sector is always controlled by the non-minimal coupling. It has nothing to do with what it's here. Gauge sector is always enter strong coupling at scales much lower than the scale graviscalar sector.
Okay, do we have one last question? 1, 2, 3. Okay, then let's think and speak again.
Thank you.
If you enjoyed the video, like and subscribe.